So in this video, I want to explain where our formula for finding the future value of an ordinary annuity comes from. And the truth is it just comes from algebra. So I want to begin by looking at a well-known rule from algebra, and that rule is that if we take x minus 1 times some polynomial x to the n plus x to the n minus 1 plus x to the n minus 2, and so on until we get down to like plus x squared plus x plus 1. So in algebra, if we multiply something like this out, that will just equal x to the n plus 1 minus 1. Now, just to kind of give an example of that, suppose I take x minus 1 times x to the 5th power plus x to the 4th power plus x to the 3rd power plus x squared plus x plus 1 and multiply that out. Now, that is what this is saying in general. So I just have x to a power, then x to the next smallest power, x to the next smallest power, and so on until I get down to x squared x1. So I'm starting with x to the 5th, then to the 4th, then to the 3rd, then to the 2nd, then just x, then just 1, and I'm multiplying that by x minus 1. And so what my algebra rule is saying is that should equal x to the 5 plus 1, so that should equal x to the 6th minus 1. Now just to verify that, let's actually multiply this out. So to multiply this out, we have to multiply each term inside the parentheses here by x, and then we have to multiply each term inside the parentheses here by minus 1. Now we haven't worked a lot on algebra in this course, but just to explain what's happening here. So x times x to the 5th would be x to the 6th, plus x times x to the 4th would be x to the 5th. X times x cubed would be x to the 4th, so plus x to the 4th. X times x squared would be x cubed, so plus x cubed. X times x would be x squared. X times 1 would be just x, so plus x. Now if I multiply minus 1 by everything in there, minus 1 times x to the 5th would be minus x to the 5th. Minus 1 times x to the 4th would be minus x to the 4th. Minus 1 times x cubed would be minus x cubed. Minus 1 times x squared would be minus x squared. Minus 1 times x would be minus x. Minus 1 times plus 1 would be minus 1. So look what happens here. Here I have plus x to the 5th. Here I have minus x to the 5th. So those cancel out. Here I have plus x to the 4th. Here I have minus x to the 4th. So those cancel out. Here I have plus x cubed. Here I have minus x cubed. So those cancel out. Plus x squared minus x squared. So those cancel out. Plus x minus x. So those cancel out. The only thing that doesn't cancel out is the x to the 6th and the minus 1. So I end up with x to the 6th minus 1, which is what we said. So as a general rule, this is going to be true. Anytime I have like x to the n minus 1, x to the n minus 2, and so on, and I multiply that by x minus 1, the result's just going to be x to the n plus 1 minus 1. Well, if this is true, if x to the 5th plus x to the 4th plus x cubed plus x squared plus x plus 1 times x minus 1 equals this, then that means that x to the 5th plus x to the 4th plus x cubed plus x squared plus x plus 1 is going to equal x to the 6th minus 1 divided by x minus 1. In other words, if this right here is true, if I divide both sides of that by x minus 1, then this part in parentheses is going to equal this divided by x minus 1. Make sense? So that's true in general. If I do the same thing for our original step, then x to the nth power plus x to the n minus 1 power plus x to the n minus 2 power, and so on, plus x squared plus x plus 1 is going to equal x to the n plus 1 minus 1 over x minus 1. So in general, that's going to be true. Well, that's what's really going on with our annuity. So let me bring back in example 1 from the previous video to demonstrate this. So here we were putting $100 in January, February, March, April, May, and so on. And so we calculated the future value of this $100, and our formula was 100 times 1 plus 0.06 divided by 12 raised to the 5th power, which ended up being 100 times 1.005 to the 5th power. And the future value of this $100 from February was the same thing, except it was the 4th power. And for March, it was the same thing except the 3rd power. And the reason why the power is going down, because for January, we had the money in there. It had been compounded 5 times. But for February, it had only been compounded 4 times. And for March, only 3 times, and so on. So what we really had going on there was that we had the $100 times 1.005 to the 5th power plus $100 times 1.005 to the 4th power plus $100 times 1.005 to the 3rd power and 1.005 to the 2nd power and 1.005 to the 1st power, and last but not least we had 100 times 1.005 to the 0 power. So this is what we had in example 1. We added these up. Now we multiplied them out to get the dollar value, but we added these up in order to get our total of $607.56. So again, if I use a little algebra here, each one of these terms has a 100 in it that could be factored out. So if I factor out the 100, then factoring 100 out of this is going to leave the 1.005 to the 5th power. Plus, factoring the 100 out of this is going to leave 1.005 to the 4th power. Plus, factoring the 100 out of here leaves 1.005 cubed. Plus, 1.005 squared. Plus, factoring the 100 out of here leaves 1.005 to the 1. But 1.005 to the 1 is just 1.005, so I'm not going to write the 1 power. And factoring the 100 out of here leaves 1.005 to the 0, but 1.005 to the 0 is just 1, so I'm going to write 1 instead of 1.005 to the 0. Well, so what? Well, this problem right here inside the brackets is like what I have right here. X to the 5th, x to the 4th, x cubed, x squared, x, and 1, except instead of having x, I have 1.005. So it's 1.005 to the 5th, and then to the 4th, to the 3rd, to the 2nd, to the 1st, and then to the 0. So this is like the x, this is like the 1 that we have right here. So by what we just said right here, this should equal 1.005 raised to the 6th power minus 1 over 1.005 minus 1. Now I still have this 100 times it. So I have 100 times. Now again, because this is like x to the 5th, x to the 4th, x cubed, x squared, x, and 1, that's going to equal x, but instead of x, we have 1.005 to the 5 plus 1 power, so that's to the 6th power, minus 1 over x, 1.005 minus 1. Now, that is 100 times 1.005 to the 6th minus 1. On the bottom, 1.005 minus 1 is just 0.005. So this is what we had in example 2 when we used the formula. So when we use the formula in example 2, let me resituate so you can compare those. We had $100 times 1.005 to the sixth minus 1, and that was divided by 0.005, which is exactly what we have right here. So if we multiply that out, that is $607.55. But my point is, this formula that we used just came from this fact from algebra. And if we generalize that and aren't just looking at 0.005, that 0.005 came from our interest rate divided by how many times we were compounding, m. So this came from 0.06 divided by 12. That's where the 0.005 came from. So if we don't use the specific example and if we generalize, we would be doing the same kind of thing. We would have the 1 plus r divided by m raised to the nth power minus 1 over r divided by m. So this is just the more general form of this. So my point is that's where this formula is coming from. It's just coming straight from algebra, and that allows us to be able to use this formula to be able to figure out the future value of the annuity instead of having to literally find the future value of each month and adding that up like we did in example 1. Now in the next video, we're going to be looking at another type of annuity called a sinking fund.